Hello, welcome back to our channel. We were discussing inverse functions and their derivatives from the chapter Transcendental Functions. Textbook Calculus and Analytic Geometry, 9th edition by G.B. Thomas and R.L. Finney. In the last video, we discussed all about one-to-one functions. So today we can see inverses. We have seen for one function, each element of x has a unique image or distinct points of x, say x1 and x2. Then it has distinct images. We can say f of x1, f of x2, like that. Like that, we can say xn maps to f of xn. Or we can say each output of one function comes from just one point or just one input. So we can reverse this function to send the output to the input like this. F of x1 we can map it to x1, f of x2 to x2, f of xn to xn, like that. This function is called the inverses, or the function defined by reversing a one function is called the inverse of f, and we denote it by f inverse. This is not f raised to minus 1, this is just a notation f inverse. See, for a function that is not 2 points can have same image, say x1 and x2 can have the same image, f of x1 or f of x. Then can we reverse this function? Then it will be like a f of x maps to x1 or x2. This will be a question mark. If it maps to two values, then it cannot be a function. So a function has an inverse if and only if it is a 1. See, if we have two sets x and y, take an arbitrary pointer x that maps to y. This is f, function f, where this is the domain of f and this is the range of f. F inverse is the function from a range of f to domain of f, like this. This is f inverse and this is the domain of f inverse, and this is the range of f inverse. We can say y equal to f maps x to y, so y equal to f of x. Or we can say x is equal to f inverse maps y to x, so f inverse of y. Can we say something about composite of f and f inverse? See, if x is the domain of f and y is the range of f, then f is the map from x to y, and f inverse is the map from y to x. F inverse is from y to x. Then what is f composite f and f inverse composite f? F inverse composite f. F inverse composite f from x to x. We can say f inverse composite f of x is equal to f inverse of f of x by definition. This function is y equal to f of x, and here this function is x is equal to f inverse of y. So we can say instead of f of x, y, f inverse of y. That is f inverse of y equal to x. Like that we can see f composite f inverse. If we have a function f from x to y, f from x to y, and f inverse from y to x, or we can say from y to x, f inverse. Then f composite f inverse is the function from y to y. F composite f inverse from y to y. Here we can say y equal to f of x, and this function x is equal to f inverse of y. Input is y and output is x. Here input is x and output is y. Now f composite f inverse of from y to y equal to f of f inverse of y by definition. F inverse of y is equal to x, that is f of x. and f of x is equal to y. That is f composite f inverse of y equal to y. Here f inverse composite f of x is equal to x. Here see some function of x is equal to x itself. Here see some function of y equal to y itself. This is called an identity function. That is f of x is equal to x is called an identity function. X maps to x itself. Here see x maps to x itself. Here see y maps to y itself. So the composite of a function and its inverse is always identity function. So we can check whether two functions f and g are inverses to one another just by checking their composition. If they are inverses, then f composite g will be identity function and g composite f will also be identity function. So we can say the result of composing f and f inverse in either order is the identity function. Identity function is the function that assigns each element to itself. So this gives a best way to test whether two functions f and g are inverses of one another. That is, suppose if we have given two functions f and g, or y equal to f of x and some y dash is equal to g of x. Then we have to find f composite g and g composite f. We will get f composite g of x is equal to x and g composite f of x is equal to x. Then these functions are inverses of one another. If any one of it is not identity function, then they are not inverses of one another. For example, we can say cube and a cube root. See, cube is y equal to x cube and a cube root is cube root of x, y or y dash equal to cube root of x. That is f of x is equal to x cube and g of x is equal to cube root of x. Then we can see f composite g of x is equal to f of g of x is equal to f of g of x is cube root of x. F of x is x cube. Therefore, f of cube root of x is cube root of x the whole cube, which is equal to x. Like that, g composite f of x is equal to g of f of x. F of x is x cube. That is g of x cube. G of x is cube root of x. Therefore, g of x cube is equal to cube root of x cube. That is equal to x. Like that, we can check whether two given functions are inverses of one another. So we can say functions f and g are an inverse pair if and only if f of g of x is equal to x and g of f of x is equal to x. In this case, g equal to f inverse and f equal to g inverse. If two functions satisfies this condition, then we can say g equal to f inverse or f equal to g inverse. They are inverse of one another. So we can write functions f and g are an inverse pair if and only if f of g of x is equal to x and g of f of x is equal to x. In this case, g equal to f inverse and f equal to g inverse. We have already discussed that a function has an inverse if and only if it is 1 1. So keep all this in mind. Next, we can discuss how to find inverse. We can see how to find inverses. Before that, in this section, we will consider only invertible functions, or we know inverse exists for only one-to-one functions. So we will consider only one-to-one functions. For example, say increasing and decreasing functions are always a one-to-one. What is increasing and decreasing functions? A function f of x increases on an interval I if for any 2 points x1 and x2 in I, x2 greater than x1 implies f of x2 greater than f of x1. Or we can say if x1 less than x2, then f of x1 less than f of x2. That is increasing function. And decreasing functions. A function decreases on I for any 2 points x1 and x2 in I, x2 greater than x1 implies f of x2 less than f of x1. That is, whenever x2 greater than x1, f of x2 is less than f of x1. That is decreasing functions. Or we can say if x1 less than x2, then f of x1 greater than f of x2. Increasing and decreasing functions are always 1 to 1. A function is 1 to 1 for any two distinct points of x, say x1 and x2. That is x1 not equal to x2, then f of x1 not equal to f of x2. That is, a function is a 1 to 1 if f of x1 not equal to f of x2 whenever x1 not equal to x2. So we can take increasing functions, take 2 points x1 and x2 such that x1 not equal to x2. We have to check f of x1 not equal to f of x2. If x1 not equal to x2, we can say either x1 is strictly less than x2 or x1 is strictly greater than x2. Since the function is increasing, we can say whenever x1 is strictly less than x2, then f of x1 is less than f of x2. F of x1 less than f of x2 implies f of x1 not equal to f of x2. So we can say f of x1 not equal to f of x2. That is 1, 1. Consider the second case. Like that, x1 strictly greater than x2 implies f of x1 strictly greater than f of x2 because it is increasing function, implies f of x1 not equal to f of x2. In these two cases, f is 1, 1. So increasing functions are 1, 1. Like that, we can say decreasing functions are 1, 1. Take 2 points x1 not equal to x2, then x1 is strictly greater than x2 or x1 is strictly less than x2. Since this function is decreasing, whenever x1 greater than x2 implies f of x1 is strictly less than f of x2. And x1 less than x2 implies f of x1 is greater than f of x2. F of x1 strictly less than f of x2 or f of x1 strictly greater than f of x2. In these two cases, we can say f of x1 not equal to f of x2. That is, whenever x1 not equal to x2, f of x1 not equal to f of x2. That is 1, 1. Consider a function y equal to f of x. We can illustrate it in a graph. Let the function be this. Okay. This is x-axis. This is y-axis. This is y equal to f of x. If we have a pointer x, how will you find the value of f at x? We will start at x on the x-axis and go up to the curve and over the y-axis and to the y-axis. That is, will go like this. This is the value of f at x. Can we read f inverse from this graph? How to read f inverse of y from this graph? See, start from y and go to the curve and find x. So we can go this direction to read f inverse of y. So this is f inverse of y. Consider the function f, that is y equal to f of x. Then this is the domain of f. Domain of f and this is the range of f. While considering the function f inverse, then this will become the domain of f inverse. And here a range of f inverse. Domain of f is the range of f inverse and range of f is the domain of f inverse. So we can say graph of f can also serve as a graph of f inverse. So we can say this is the graph of y equal to f of x and also x is equal to f inverse of y. Here we are reading the graph in the reverse process, x is equal to f inverse of y. Now we can try to draw this graph x is equal to f inverse of y in the usual way. Here the domain in the y-axis and the range in the x-axis. We can just change. We can just make domain in the x-axis and range in the y-axis. The graph will be like this. X is equal to f inverse of y. And this is the domain of f inverse and here range of f inverse. Here if this is the point x0, then here the point will be 0x. And here if this is the point AB, this point will become BA here. Say this is B and if this is A, we can say this is the point BA. See, if f is the function that sends x1 to y1, x2 to y2, then what is f inverse? F inverse sends y1 to x1, y2 to x2. So if x1, y1 is a point in f, then it will become y1, x1 in f inverse. So if a, b is a point in f, it will become b, a in f inverse. This will be reflection of the line y equal to x. If this is the line y equal to x, that is the point 0, 0, 1, 1, 2, 2, 3, 3, etc. If this is the line y equal to x, then this graph is the reflection of f in the line y equal to x. You can place a mirror in this line y equal to x. Then you will get f here. If you place the mirror in this, we can get f inverse here. You can see the magic using mirror. So we can say graph of f inverse is the reflection line y equal to x. F inverse. F inverse is the reflection of the line y equal to x. Here we have written x is equal to f inverse of y. Instead we can write y equal to f inverse of x. We can just reverse. We can write y equal to f inverse of x. We can just interchange the variable, no change. So we can say that in the graph of f and f inverse, input and output pairs get reversed. We can portray the graph of f and f inverse in the same graph, but here a domain and range will change. To display the graph in the usual way, we have to reverse the pair and we just reverse the pair by reflecting the graph on the line 45 degree y equal to x and interchange the letters x and y. So we can say the graph of f of x and f inverse of x are symmetric about the line y equal to x. If we draw the graph of f in this same graph, it will be like this is a rough sketch. It will be symmetric about the line y equal to x. So to find f inverse graphically, we can just reverse the pair. All the points we can just reverse the pair by reflecting the graph in the 45 degree line y equal to x, the line y equal to x, and interchange the letters x and y like this. Otherwise, if we have a function y equal to f of x, just express x in terms of y, that is x is equal to f inverse of y, then interchange x and y so that we get y equal to f inverse of x. We can see more examples. Example, find the inverse of y equal to 1 by 2 x plus 1 expressed as a function of x. Here the function is y equal to 1 by 2x plus 1. Is this function invertible? You can see this is an increasing function, so 1 1, therefore inverse existed. You need not to check it always. So to find the inverse, a first step is solve for x in terms of y. We have to find x in terms of y. And the second step, interchange x and y. So we can see x from this. Here we will get y minus 1 is equal to 1 by 2x, or we get x is equal to 2 into y minus 1. or 2y minus 2. So this is x. Next we can interchange x and y. Then we will get y is equal to 2x minus 2. So this is the inverse. If this is the function y equal to f of x, then we can write f inverse of x is equal to 2x minus 2. We have studied composite of f and f inverse will give the identity. So we can check whether this is true. So we can see f composite f inverse and f inverse composite f. F composite f inverse is f of f inverse of x. This is equal to f of f inverse of x is 2x minus 2. F of 2x minus 2. F of x is 1 by 2x plus 1. So f of 2x minus 2 is, instead of x, substitute 2x minus 2. This we will get 1 by 2 into 2x minus 2 plus 1. That is equal to 1 by 2 into 2x minus 2, 2 taken outside, x minus 1 plus 1. 2 get cancelled. This is equal to x minus 1 plus 1. This is equal to x identity function. Like that we can check f inverse composite f. This is f inverse of f of x by definition of composite function. This is equal to f inverse of f of x is 1 by 2x plus 1. This is equal to f inverse of x is 2x minus 2. Therefore, f inverse of 1 by 2x plus 1 is, instead of x, put 1 by 2x plus 1. That is 2 into 1 by 2x plus 1 minus 2. This is equal to 2 into, this is x plus 2 by 2. X plus 2 by 2. Denominator making common. 2 get cancelled, minus 2. This is equal to x plus 2 minus 2 x. So f composite f inverse of x is equal to x. That is identity function. And f inverse composite f of x is equal to x identity function. So this is true. Now we can try to draw this graphically. Okay. We can find the points. For f, when x is equal to 0, what is y? 0 plus 1, y equal to 1. When x is equal to 2, 2 get cancelled, 1 plus 1, y equal to 2. 2. When x is equal to minus 2, minus 2 by 2 is minus 1. Minus 1 plus 1 is 0. So the point minus 2, 0. And when x is equal to 4, the point is 4 by 2 is 2. 2 plus 1, 3. 4, 3. Here minus 4. Minus 4 by 2 is minus 2. Minus 2 plus 1 is minus 1. We can draw the graph. Points are minus 4, minus 1. Here minus 2, 0. 0, 1. 2, 2. 4, 3. So this is the graph. Y equal to f of x. To draw y equal to f inverse of x, we can just reverse these points. So minus 1, minus 4. Minus 1, minus 4. 1, 0. And 2, 2. And 3, 4. Just reverse the points. Then the graph will be like this. This is the graph. We can draw y equal to x also. 0, 0. 1, 1. 2, 2. 3, 3. And 4, 4. Like that here. Minus 1, minus 1. Minus 2, minus 2. Minus 3, minus 3. This is the line y equal to x. So drawing together, you can see that f and f inverse are symmetric with respect to the line y equal to x. Next question, find the inverse of the function y equal to x square, x greater than or equal to 0, expressed as a function of x. Here the function is y equal to x square, x greater than or equal to 0. Why we are considering x greater than or equal to 0? If we take negative values, see minus 2 square is equal to 4 and also 2 square is equal to 4. So this will not be one-to-one function. So inverse does not exist. So we are considering only x greater than or equal to 0. Then only this function will become 1, 1. So to find inverse, first step is solve for x in terms of y. So we will get, taking square root on both sides, we get a root y is equal to root x square. Root x square is equal to, we can say x. Instead we can say mod x. We are taking only positive values. So y equal to root x. Next step, interchange x and y. So we get x is equal to root y. So if this is the function y equal to f of x, then f inverse of x, we can say f inverse of x is equal to root x. We can try to draw this graph. The points are y equal to x square. When x is equal to 0, y equal to 0. When x is equal to 1, y equal to 1. When x is equal to 2, y equal to 4. 3, y equal to 9. So the graph is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the points are 0, 0, 1, 1, 2, 4 and 3, 9. So this is the graph of y equal to x square. The positive x-axis will go like this. So this is y equal to x square, or this is f of x. Now we can draw f inverse of x. Just reverse these points. So we have 0, 0, 1, 1, 4, 2, and 9, 3. So this will be the graph of y equal to root x. We can draw the line y equal to x also. 2, 2, 3, 3, like that. So this is the line y equal to x. We can discuss many more exercises to become the concept very much thorough. We can see more exercises on the next video. If you find this video useful, please like, share and subscribe. Thank you for watching. Thank you.